Okay, recording has started. And also, I graded the new homework that was turned in on Thursday. The homework from the previous week, I went through a number of those thinking that they would all be updated, but many of you hadn't updated. Like, if you don't have a grade on a homework from a previous week, that's going to wind up going in as a grade of 0. So if it asks you to, like, finish something up or redo a certain problem, please get those done by the end of each week. So from the previous week, there were a number of things that were still the same, and so you still don't have a grade recorded. Um, I'll check in on those from the previous week, and then I'm going to start assigning zeros if you don't have the what's requested. You could still afterwards change it, but I won't hold you to that 0, but that's what's going to be there if you don't eventually get that into me. So I'd like to get those all in at the end of each week. All right, so start on practice quiz, just problem number 1. Write that definition of f prime of a from memory. Don't look it up. All right, and let me write that in. F prime of a is the limit as h approaches 0. F of a plus h minus f of a all over h. Okay, and then it's not on here, but I want you to complete this picture. If this is my function, this is a, this is the function f, mark this, and show what this limit is referring to in terms of this picture. So let me give you a quick minute to get the visualization of this definition. And a quick question I have. In Discord, when I first get on and I first set up the voice channel, the live feed, can you all hear me right away, or do you have to wait until you get into the live feed and connect up? And so should I pause for a minute or so to make sure everybody's...
As long as you're in the general chat voice channel, you can hear, and then you can join the stream whenever you
Okay,
press
so
join stream.
people should join the general voice channel right away.
Yeah.
And then when I start the live stream, they'll hear me right away, even if they haven't.
Well, if you're in the voice channel as well, we can hear you We just can't see anything until you initiate the live stream.
Okay, but you've got to be in the voice channel too. Okay, because I think there was only a couple people in the voice channel. You were one of them when I first got in. All right, that makes sense. Thanks. All right, does anybody need more time on this? All right, then, this is A plus H, this point right here, come on, is A f of A. This point here, its two coordinates are A f of A plus H. And then what we're trying to find is the slope of this tangent line. And what we're going to find on this first expression is the slope of this line. And because this is the difference in the y coordinates divided by the difference in the x coordinates, a plus h minus a, the a's cancel out and you're just left with h. So this is really a change in y over the change in x. And then the limit as h approaches 0 just brings this second point in closer to this point. And the closer you bring it in, the better the estimate. And as you keep bringing it in closer, you get closer and closer to the red line. Okay, now that's reviewing the basic fundamental concept in all of calculus, the derivative, and its visualization. Now we're going to change to the standard definition. So from here on, we're not going to say that the derivative is called f prime of a anymore. The standard definition is now different. And it's exactly the same as this, but all the a's are going to be replaced with the letter x, f prime of x. And when I say the standard definition of the derivative, this is what I'm going to mean from now on. And remember, there were two of them, one with the h and one without the h. We're going to only use the one with the h. So it's going to be this, the limit, as h approaches 0, f of x plus h minus f of x. So the x's are just replacing the a's over h. Now, you might ask, hey, isn't that the same thing? Because can't any letter be replaced? Couldn't you just replace A with B or C or D? It doesn't matter. And that is true. As long as that same letter shows up here and here, the X showing up here and here, it doesn't matter. It all means the same thing. But there's a convention. The convention in math is that we tend to use the early letters of the alphabet, A, B, C, for constants, things that are fixed. And that's how we first imagined the derivative. Like we were trying to find out what is the slope of y equals x squared when x is equal to 3. And we first did it with 3, and then we generalized it to a, but we were still thinking of a as a fixed constant, some number that we just didn't know what number it was. Maybe it was 3, maybe it was 4, or something like this. When we use letters later in the alphabet, like x, y, and z, we tend to mean variables, things that vary, not are fixed constants. And so, although they mean the same thing in one way, the convention is we are now looking at as a function of x. And then when you look at this as a function of x, we tend to think of, two functions that are related. One represents the heights of the original function, one represents the slopes of the function. And so it's a different conceptual point of view, and we introduced you to that conceptual point of view last section, 3.2, when we had to graph the function and then graph the derivative of the function, getting you used to both our functions of x. And now we changed the standard definition of the derivative. From now on, it won't change anymore. This is it. Memorize this, and it's the only thing you have to memorize for the basic definition of the derivative. Okay, now when we do this, the picture slightly changes. So, not much though. Here's my function, and here is x plus h, directly across from this point, f of x, directly across from here, f of x plus h. So this point, its two coordinates are x, f of x, its two coordinates, x plus h, f of x plus h. So you can see that if we take the difference in the y coordinates, we get the numerator over here. The difference in the x coordinates, we get the denominator over here. The limit as h approaches 0 pushes this point towards this point. We still are going to go for the tangent line, and we're going to wind up getting better and better secant lines that will approximate it. All right, so number 3, without computations, state what f prime of x is. So very quickly go here and say, all right, f prime of x, do it without any computations, think of more what does it represent, and get an answer for each of those 3. I'll give you a quick minute. Okay, anybody need more time? So f prime of x on this first one is 3, because that's a line of slope 3, and the slope is always 3. This is a horizontal line at height 7. Slope is 0. This is a horizontal line at height of 0, but its slope is still the same, which is 0. So by just understanding that it's the slope, we can quickly get these results. We don't have to do any computations to get them. When we go to number 4, y equals x squared, find the derivative using our new definition right up here. So this one you're going to have to do the computations. You're going to have to simplify the fraction on down so you get the h's to cancel, and give you a minute. So you start with the definition from number 2 and work that through. anybody still need more time on number 4? All right, let's go then. F prime of x. Limit as h approaches 0. F of anything is that thing squared. You get two middle terms. I'll put them in alphabetical order. 2hx plus h squared minus x squared of h. Now, these x squareds cancel out. These what's left is these two terms that both contain an h. And then the h's will cancel. Now the form is 0 over 0, right up until the h is canceled. Once the h is canceled, it is no longer 0 over 0. Now as h goes to 0, it will drive the h to 0. And then, since this thing is going to go to 0, we're going to be left with 2x. And that's it. And we had seen this before. If f of x is x squared, f prime of x is 2x, and that tells us that if we had any parabola where if this is 1, then the slope here is 2. If this is 2, the slope there is 4. If this is 0, the slope is 0. If this is negative 1, the slope is negative 2. It's negative 2, the slope is negative 4. It tells us the slopes at every single point on this. Alright, so let me pause at this point. Give me feedback on anything in problems 1 through 4, which you're strongest at, which you need more practice at, if you're good with everything. Just let me know where you're at in the text channel here. Okay. I'm wondering if the graphing part being a more difficult part is kind of common. I would kind of expect that. Alright. So, okay, and number 4 is new because it's a new definition. And, alright, let's go to number 5 now. Below is f. So that's a piecewise function. Draw a graph of the derivative f prime on the same grid. So, I'll give you a minute on number 5. Okay, anybody need more time?
I do.
Okay, take your time. Okay, 30 seconds more. All right. So we can see that this graph, the natural dividing lines are -5 and x equal -1, x equal +3. That's when all the rules change. To the left of -5, the slope is always, well, we're going downhill. Every time we go to the right one, we go down one. The slope is -1. So the derivative is -1 over here. Now, the derivative won't exist whenever we have a discontinuity. Any type of discontinuity, whether it's a hole or jump discontinuity or a vertical asymptote, the derivatives won't exist at those points. Okay. Then, between x is -5 to x equals -1, it's horizontal, slope of 0. So I'm going to have open circles, slope of 0. Between x is -1 and x is 3, the slope is 1. Between 3 and on, the slope is back to -1 again. Every time it moves to the right one, it goes down 1. Like this. Now I'm kind of assuming that this didn't have anything at the end like an open circle or a filled in circle. So very often they mean it goes on forever. They weren't really clear. But if they meant that it goes on forever, then it would be like this. All right, give me feedback on this. And your feedback could be, I couldn't get it, but I really understand it now. Or, I couldn't get it and I still am struggling with it. Or, oh, it was easy for me, But on the graphing part, I'd like to see where you guys are at on number 5.
I have a question.
Yes.
So when we're drawing the derivative on the same graph,
Yeah.
will all the points be an open circle?
All the places where the original function is not continuous, like in the gaps in between, yes, those will all be open circles. You'll never fill any of those in. And the other points that will be open circles as well would be if you had a cusp point, like that. Remember those where it takes a sharp turn? The derivative won't exist there, so the derivative function would have an open circle right at that point as well.
Okay.
And let me just take a quick look. Okay, that's kind of what I was thinking, that there's some people who need some more practice with the graphing. It can be a little difficult getting used to that. All right, let's go to number 6. Below is f. Draw a graph of f prime on the same grid. Anybody need more time? All right, let's look at it. So remember the first steps. Step 1 was find out where f prime is equal to 0. Horizontal tangent lines of f are x-intercepts of f prime. So here is where it's horizontal. Here is where it's horizontal. There's only 2 places where the tangent line is horizontal. And so there's only 2 x-intercepts of f prime. There and there. So let's go in between these 2. So the second step is between x-intercepts of f prime. So on this green curve that I'm going to be drawing, we must be entirely above or below x-axis. So between here and here, the slopes are going to be always negative or always positive. It can't be both, because if it was both, it would have to go through 0 and there'd be yet another x-intercept. There's only 2 x-intercepts of this. And the slopes, well, if you bought stock in this company, you'd say, man, I could have bought it over here and I've been doing great. Here I've been doing great, but what did I do? I bought it at its highest point and sold it at its lowest. Terrible. I lost money, so the slopes are negative the whole time. So between these 2 points, I need negative. And notice it's 0 but getting more and more negative. It gets about the most negative. Or if you were a skier skiing down this, suppose you're a beginning skier. When are you going to be most scared? When you're the steepest, which is about halfway between these 2 points. And then it's not so steep on either of the ends. So the steepest it ever is maybe, I don't know, -1, -2, something like this. So it's going to go something like this. And then to the right of this, it's got to be all above or all below the x-axis, but the slopes are all positive, getting steeper and steeper and steeper. Over here, the slopes must be all positive or all negative. Again, if you bought stock in this function, you'd be happy anywhere over here because it was going up. And the further you go to the left, the steeper it gets, bigger and bigger slopes. Like this. And we also are seeing a tendency that a third degree original polynomial, the derivative, tends to be 1 degree less a second degree. Instead of a y equals x cubed curve, it looks like a y equals x squared, a second degree polynomial curve. All right, this one is a fair amount tougher than just the straight line segments. Give me feedback on this one. All right, and the feedback could be, I couldn't get it, but I understand it, or all that kind of stuff. But give me some details. Okay, now it's also true, from what we have so far, and we're rough estimating, is you wouldn't really be sure if it's supposed to be a curve or maybe straight line segments. You don't have enough information to really get that over here. But that you get these 2 points because they come from horizontal tangent lines. Those become the x-intercepts. And in between them, you're all on one side of the x-axis and you put it on the correct side. But if you made like a V shape here instead of a parabola shape, that would be okay. But the main thing is you can get these x-intercepts for f prime, and you can get below it in between here and above it on the 2 extremes. And over there and there.
If you made a V shape, would that not suggest that your slope was either increasing or decreasing at a constant rate, though, or?
It gets kind of tricky with that. Notice if you take the derivative of a parabola function, its derivative is going to be a straight line, and so it's hard to tell those subtleties from here, and I wouldn't anticipate that you could get those all correct. All right. Let's go now to questions on homework. Okay, any specific questions?
Could you do 57 B?
Okay. So 3.2. B. This is page 151. I think I'm going to have to log back in here. No. Okay. All right. Explain why or why not. Determine whether the following statement is true. Give an explanation or counterexample. The function f of x's absolute value of x plus 1 is continuous for all x, but not differentiable for all x. right. Let's simplify that a little bit. Suppose it was just this. The shape of this is like this. 45-degree angle lines, like this. And then when you have this, this is going to push you in which direction? Up, down, left, or right? Anybody?
Left.
Left. 1 unit. Because it's replacing the x with x plus 1. Horizontal transformations go opposite direction of sign. It would be the same graph, but you would have the bottom of the V over here to the left 1 point. Now, they're saying that this is continuous. Does this look continuous? Could I draw this thing without ever lifting my pencil? Yes. So it is continuous. But it is not differentiable for all x. And that is true because it has what we call a cusp point, where it takes a sharp turn right there. The instantaneous tangent line from the left is -1, while from the right, its slope is +1. So this is true. Does that answer your question? Whose question was that?
That was mine. I think I'm not understanding what differentiable means.
Okay, let's clarify that. So differentiable means that the derivative exists, that you can take the derivative. And remember, the derivative is a two-sided limit. Its definition is now, here's the standard definition for it. But you can approach h from the left or h from the right. And so the slope, the instantaneous slope, has to be the same from the left side and from the right. But if you approach 0 from the left, you approach 0 from the right, you're going to get two different slopes. So it doesn't exist. Does that clarify, Kylie?
So the slope has to, the limit as h reaches 0 has to be the same on both sides.
That is correct. And in this case, I didn't draw the shape of this one. So it's really as x approaches -1 over here, that's where the problem is going to be. It's not, the derivative won't exist when x is -1. Any other questions?
There's two. Dorado asked for number 50 and Alondra asked for number 64.
Okay. Let's go to number 50. Okay, so the graph of the derivative. Okay, so I'm going to make the derivative graph here. And the first step is, where do I have horizontal tangent lines? Horizontal tangent lines. And there's none. Horizontal tangent lines. Nowhere. So that was my first step, so I feel kind of lost. And then I would look in between the horizontal tangent lines and then say, oh, in between them it has to be all above the x-axis or all below the x-axis. But I'm stuck because of this very first thing until I start to realize hold on, if there's no horizontal tangent lines, remember what the horizontal tangent lines, that's a transition from negative slopes to positive slopes or vice versa. So there's no transitioning. So the slopes must be all positive or all negative. So thus I must be entirely above the x-axis for f prime or entirely below the x-axis for f prime. So let's go look at this. What are all the slopes? Are these, if you bought stock in this company, are you happy or sad? You're going up the whole time. Your slopes are positive all the time. So what does this mean for my derivative? My derivative is going to be above the x-axis the whole time. Now, there's lots of ways, though, I can be above the x-axis. I could be above the x-axis, kind of like this. That's above the x-axis the whole time. Could that possibly be the slopes?
No,
Why not?
because that line indicates that it's steepest at the end, at the beginning and the end of the slope.
Very good, very good. See, the heights of this slope is how steep we are. And this is saying that we're not very steep in the center of the graph, but we're getting steeper on, but that's the opposite of what's true. Let me, hold it. Let me just do Control Z. All right, let's go. So it's steepest in the center. Now, the steepest point right here, its slope might be like every time I go to the 1 to the right, it might go up 3 or so. Maybe it's like up to this high. But then as I fall over here, I'm getting more and more horizontal. As I fall to this side, I'm getting more and more horizontal as well. See how you kind of... But it still seems to be positive the whole time. So yeah, I would think something like this. See how I'm staying above the x-axis the whole time, and I'm steepest in the center, and getting more and more horizontal the more I move to either edge, like this. Any questions on number 50? All right, let's move on. What was the other one?
Number 64.
64. Got to sign back in. And that's page 152. So let's look at 64. A line normal to another line, or to a tangent line, is often called a normal line. Find an equation, a line perpendicular to another line. So find an equation of a line perpendicular to the line that is a tangent of the following curves at the given point P. Alright, so let's go up to where we have a grid, and let me just show you. Suppose I have a line that has slope 2. Every time I move to the right one, it goes up 2. Alright. To be perpendicular to this, if I just made that negative, like negative 2, every time I went to the right one, I went down 2, that would not be perpendicular to that. It's too steep. It's more than a 90-degree angle. To be perpendicular, you do have to change the sign. So if it was going uphill, it's now got to go downhill. But you have to change the thing that was more steep has now got to become more shallow. The more vertical it was, the more horizontal the new line has to be. So we have to turn around. This one had a slope of 2 over 1. The new one's going to have a slope of negative 1 over 2. It'll be negative, but every time it goes to the right 2, it'll go down 1. So that's going to give me perpendicular 90-degree angle between the two lines. Right here. So slopes that are perpendicular have the rule that they are negative reciprocals of one another, or if you multiply them together, you get a result of negative 1. So we do everything the same as we did before, is find the equation of the line perpendicular to the line that's tangent. This is actually saying, normally we're used to the question, find the tangent line, the equation of the tangent line. And I'm going to do it exactly the same way, except after, so step 1 is, let me type this out. It'll be a little faster. Step 1, find the slope at P. Then, after you find the slope at P, you could find the equation of the tangent line, but that's not what they ask. Take the negative reciprocal of the slope. Then use the point 4,2 and this negative reciprocal to find the equation of the normal line. All right, so that's what I'd like to do here, is just give you that hint and then not do the problem for you. But that might have been disorienting for you because of this new terminology and all that stuff. But that's all I really want to say on number 64. And is that it for questions? All right, let's go to 3.3. We'll just get started here before we take our break. Rules of differentiation. And by the way, this practice quiz, number 4, we found the derivative of y equals x squared by the definition, and we came out with 2x. When f of x is x squared, f prime of x is 2x, and how we got that was by using the definition of the derivative and the limits. All right. Where we're headed in this new section is we're going to learn some incredibly huge shortcuts where you're going to be able to take the derivative of something basically instantly. Instead of going through that limit and all those steps, you'll have this rule that's so powerful. you'll have the derivative instantly. And some people get very excited about this. They say, oh my gosh, there's giant shortcuts. And some people get frustrated. They say, well, why did we have to learn this other way with the limit if we're just going to replace that with this giant shortcut? And the answer to that question is, that's an important question. We're not going to abandon the definition. It'll still be important that you know how to get the derivative by both methods using this huge shortcut that we're going to learn today, and by using the definition of the derivative and writing out that limit and reducing, getting the h's to cancel out. And much of the theme of the rest of this calculus class will be taking the derivatives and using the derivatives and seeing what the derivatives tell us for a bigger and bigger variety of functions. But when we come up to something new, a new type of function that we've never applied it to, we'll have to constantly refer back to the definition of the derivative and then develop new shortcuts for different types of functions. We're going to learn some shortcuts, but they only work for particular types of functions. And when we get other types of functions, we got to have a whole different set of rules, and I'll have to keep going back to the original definition each time. All right, so that's kind of where we're going today, is some big shortcut rules. But let's start out with Leibniz's notation. Remember, Newton and Leibniz, the two discoverers of calculus. Newton used the notation, instead of a prime, he did this f hat. And that little bar just got turned sideways, kind of stuck at an angle, and called f prime. And it's a very common notation. Leibniz used a different notation. All right. Instead of f prime of x, he used dx of f of x. So dx means take the derivative, but it's a little more specific than Newton's notation. It says take the derivative with respect to the letter x. So it tells you what the independent variable is. Now that becomes really handy at certain points, particularly handy when we get into calculus 2 and calculus 3, when we get functions that have several input variables, and you'll have to know with respect to what variable. We'll go back and forth using these two different notations. We'll use both notations very often. There's other variations of this. dx, take the derivative with respect to x. Now f and y are pretty interchangeable. We often use y instead of f of x. And then this has gotten to become shortcut notation, dy dx. So all three of these formats we'll be using regularly. The derivative as d dx, d dx of y, and then you can kind of think of this as like if you were multiplying these two things and you made y over 1, and then 1 times dx would give you this, and these d and the y would go together. That's really moves up into the top over there, dy dx. One of the advantages, particularly we see it with this last format, dy dx, is Leibniz knew that the slope whether it's an instantaneous slope or any kind of slope, it'll act as a fraction. And it's basically the change in y over the change in x. And when he did dy dx right here, he winds up getting to use the fractional aspect of this. And we'll eventually split those up, and we'll use dy and dx separately, and we'll see how the new Leibniz notation gives us several advantages. And when things get really tough, we tend to go to Leibniz notation because of its greater degree of specificity about derivative with respect to what, and it looks like a fraction, and we'll be able to utilize that it looks like a fraction. All right. The second intro topic today is binomial expansion. All right. When we have something like x plus h to the second power, we know we have to FOIL it out. You can't just distribute the exponent and make it x squared plus h squared. You got to do x plus h times x plus h, and you got to make all those arrows and get the two middle terms. Okay. Now we're going to expand this out so that we can eventually get a rule for what does x plus h to the fifth power or to the eighth power, something, how does it expand out? And we need a shortcut for expanding out something like this to large powers. And we're going to take a break right now, and then when we come back, we'll start with this binomial expansion, and I'll explain how we can come up with a shortcut for expanding. We call it binomial because two terms, like x plus h. Expansion means get rid of all the parentheses. And how would I get rid of all the parentheses in something like this without having to FOIL it out 5 times, which would be a nightmare? Okay. And we'll just show the beginning of that process because the beginning is all we'll need. So let's start again at 12:45, and I'll hang around for a minute or two here. If you had a question on anything that was marked on your exam, you didn't understand what you got marked wrong for, you can ask now. Would be a great time to do that. Otherwise, I'll see you at 12:45. Okay, we will start again, and I'm going to be on the whiteboard. So x plus h squared. We typically think of this as this double distributive. But if we think of it only that way, we'll never be able to get to where x plus h to the 12th power. We'll know what the first term is going to be, what the second term is going to be, and we'll never be able to get a shortcut. We want to get a shortcut for this stuff, and we'll see in a little while why that's so important. All right, so another way that we can think of this x plus h squared is look at it a little more statistically. What I'm going to do is whenever notice that there were 4 different terms that came up right from here. And the 4 terms came up from, you had to pick one and pick one each time. Each of the 2 terms, you had to pick one from the first set and one from the second set. You couldn't pick this one and this one to multiply together. It had to be this one times either this or this. And then this one times either this or this. You wind up picking one from the first set and picking one from the second set. Now if you look at it in this way, we can see that the x squared term came about from picking x both times. So when you were in the first set, you picked x. When you were moved over to the second set, you picked x. The h squared term came from picking h and picking h. Now, the other 2 terms came from picking one x and pick one h. Pick one x, pick one h. But there are 2 ways to do that. You could pick your x in the first set, and then of course your h would come from the second set. Or you could have picked your x from the second set, and then the h would have had to come from the first set. So there were 2 different ways that you can pick one x and one h. And that's why the hx term has a coefficient of 2 in front of it. So we picked one of each, and we got it. It's a different way of looking at it, but this is a way that can extend to something like this. Alright, so before I run to this, let's make sure that you guys are okay with this. Give me a little bit of feedback. Is this making sense, or need a little more clarification on this before I move over to x plus h to the 5th? Okay. Alright, so let's come back here. X plus h to the 5th. We gotta write this out 5 times. All right, now, when you do this expansion, we know the first term is going to be x to the fifth, and that's going to come from picking x each time. Every single set I picked the x, and I got x to the fifth. The next one is going to be, I'm going to pick 1, I'm going to slowly decrease the power of x. So instead of x to the fifth, it's going to be x to the fourth. But if I pick the x only 4 times, that means one of the times I had to have picked h. So I'm going to be picking h once and x 4 times. Now, that's the same as just saying we'll just put all our attention is pick h once. Because if you pick h once, it means all the other times you had to have picked x. Now, how many different ways can you pick h once? Can anybody tell me?
5,
Why 5?
because you have 5 sets and 5
That's right.
H's in each set. H.
Totally right. You could have picked this h, or you could have picked the second h, or the third h, the fourth h, or the fifth h. Any one of those. There are 5 ways to do this. 5 different h's to choose from. So that's why this is going to have a coefficient of 5. And then the next terms after this would be h would, the x would keep decreasing by 1. The h would keep increasing by 1. So the sum of the exponents would always be 5. This would be some coefficient. We'd keep doing this. H would decrease by 1. X would decrease. H would increase by 1. X would decrease by 1. And it would be another different coefficient. H to the fourth, x. Now this one, we know its coefficient would be 5. Because once again, we would be picking x only one time, but there's 5 different x's to pick from. And then the last term would be no x's at all, h to the fifth, but there's only one way to pick h's every time. And it would look like this. Now there's a couple unknown coefficients in here, and it turns out that's not going to be important to us. The only ones that are really going to be important to us is these first two. If we understand this binomial expansion just this far, that's all we're going to need today. And what is this number? It's always the same as this exponent. So if I had x plus h to the 11th power, this would be x to the 11th, picking x every time. There's only one way to do that. H one time, x all the other times. But how many different ways are there to do it? Well, I would have x plus h written out 11 times, so there's 11 different h's to pick from. So whatever that exponent is, that becomes the coefficient of this. We get this. In other words, if we totally generalize this, it's x plus h to the nth power. The first term is going to be x to what power? X to the nth plus the next term. Can anybody tell me what's going to be this next term?
Yeah, it's going to be n times the quantity x plus h to the 10th term. No, sorry, to the n minus 1 term.
H will be to the first, and x will be to the n minus 1. That's right. This decreases by 1. The exponent here always becomes the coefficient right here. You get 1h, and then that decreases by 1, and then plus da 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 da. All right. If we know that much about the coefficient of expansion, the binomial expansion, then we have enough for what we need. So let me put this into the notes. And let's erase this. Now we're going to take functions and their derivatives, and we're going to look for patterns, and we're going to try to come up with a giant shortcut. All right? We are aiming for a giant shortcut. For taking derivatives. And we have two things that we're going to look at to get this giant shortcut. Number one, we'll look at properties of the derivative. And two principal properties I want to point out. A. Now I'm going to use Leibniz notation. D dx for the derivative of c times f of x. Well, we're kind of familiar with this already. We'd seen this with limits, that constant just gets to come out front. And it does the same thing for the derivative. So, in words, we would say the derivative of a constant times a function is equal to a constant times the derivative of the function. And that's a really powerful rule that will really help us out. Second one, the derivative of the sum of two functions. Later I'm going to put a minus here, so I'm going to put that up a little higher. It turns out to be the derivative of a sum is the sum of the derivatives. Okay. Now, that also holds true if there's a minus sign. So we come back later and we put a minus sign and a minus sign. Either one works. Derivative of the difference of two functions is the same as the difference in the derivatives. Right. Now, number two. We're aiming for a giant shortcut. We're going to look for patterns. And we're going to make a little table. If I have f of x and f prime of x, if I have f of x being x squared, we're going to say, well, what was f prime of x? Now, we had done this one, and we're going to look at when f of x is x cubed, what's f prime of x? When f of x is x to the fourth, what's f prime of x? And then we'll try to look at the general patterns that exist in how f prime relates to f, and then maybe we can come up with a shortcut. Now, this will only work for functions like this, but if you combine it with these two properties, it can help us to do a whole lot of things. If I take, f of x is equal to 5x to the fourth minus 3x squared plus 2x, if I could have a shortcut for derivatating these, I could have a shortcut for derivatating that whole expression with these two properties combining them. So, f of x equals x squared. We did that already today in the practice quiz. Look back at your notes. What did we get when we took the derivative of x squared?
It was 2x.
We got 2x. All right. Now, we'll try to look for patterns. It's hard to see a pattern if you just only have one entry in your table. Let's do x cubed next. So if f of x is x cubed, let me come way over here. F prime of x. Now, we write out by memory, the derivative f prime of x is equal to a limit. So let me give you a moment to get ahead of me, because that's what we do every time we have to write it out. We make sure that we don't look it up until we guess it first, and then you'll find that you'll have it memorized really quick. So let me just give you 10 seconds to write that out from memory. So there it is. And then we're going to actually work this out. Now, this is the limit as h approaches 0. We're going to get x plus h cubed minus f of x is x cubed over h. Now, you see why we needed to figure out a shortcut for this binomial expansion? All right, so let's look at this. This is going to be the limit as h approaches 0. We said that when we FOILed this out 3 times, what are we going to end up with? X to the 3rd power was our first term. And there's only one way because you're picking x's each time. And then, what was the next term going to be? It was, yes.
3x squared, or 3x squared 8.
Yes. I'll put that h first. And just, I like to put them in alphabetical order. And then x squared. Because this was always the same as this one. Because you write out x plus h 3 times. And you're picking h once, well, you have 3 different choices for your h. And then you're going to get more terms, but it doesn't matter what the coefficient. I'm just going to put a question mark, h squared x, plus the last one I know is just going to be h cubed minus x cubed over h. Now, how come the question mark can be left as a question mark? Well, let's look. X cubes cancel, and I need this h to cancel. Before I can cancel with this h out, I have to factor it out of all these terms. When I factor out that h, question mark hx plus h squared over h. Now, these are going to cancel. And then what's going to happen is, the reason why it didn't matter what this question mark was, is when h goes to 0, this whole term gets driven to 0, as with this one. So no matter what number was there, it's just going to go to 0. The only thing that's going to be left over as part of my answer is this first term, the one with, it is actually the second term of the binomial expansion, because it's the only one that'll have a single h. It'll always be this first term canceling with this last term, and then the one with the single h will be the only survivor. All the rest of those terms will get driven to 0. And so this is going to be, when you drive it all those to 0, your limit is going to be 3x squared. And that's it. So now we take this answer and we transfer it over to here. All right, now that we have 2 rows, we might start to see a pattern. Everybody take a moment and take a guess as what you think is a reasonable thing that might appear in this column across from x to the 4th. So go into your group and do the chat thing in your group and see what, and I'll call on a group in a moment. What might be a possible result if we were looking for some kind of pattern there? X to the 4th here, what's coming up over here? I'll give you a minute. Okay, make sure that the leader of the group has appointed a speaker for today. All right, group 2, what might be there in across from x to the 4th? Any ideas?
We chose 4x cubed.
It's Rachel, and it's 4x cubed.
Yes.
All right. Let's see it, if that is correct. Now, what we're kind of, by putting 4x cubed in there, is the pattern that you're kind of using is whatever was the exponent is the number out front. Whatever is the exponent is the number out front. Exponent, number out front. And then the new exponent is going to be 1 less than the previous exponent. So that seems like a pretty reasonable pattern. So let's go ahead and do this again. and see if that is correct. So to do this again, I'm just going to erase this, and then this, and then from here, everything's going to change significantly, so I'm going to wipe out all the rest of that. So if I have to the fourth, to the fourth, and to the fourth, and then the limit, h approaches 0. And if I FOILed this out 4 times, my first term would be x to the fourth. Then I would get a coefficient of 4, a single h, x cubed, plus, I'm just going to put dot, 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 because I don't care, minus x to the fourth over h. Alright, and then this is going to equal the limit as h approaches 0, and the x to the fourths kill each other off. The only other ones in here all have h's. Let me put one more term in here, even though I don't know its coefficient. It's going to be h squared x squared plus da, 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 over h, which is equal to the limit as h approaches 0, and all of these have an h in them. And then the h's divide out. The form was 0 over 0 until they divided out. The instant they divided out, it's no longer 0 over 0. Now we can send h to 0, and it'll send every one of those to 0. And all I'll be left with is 4x cubed, which is exactly what we had right here. And let's go furthermore then. Suppose I had x to the nth power. Alright, once more, go into your groups. What do you suppose is going to happen to the right side of this? And this time when you're in your group, if you think you know the answer, don't put it in right away. Check on other folks and see if somebody else can kind of work their way to the answer. And if you're kind of guessing, you're not totally sure, put your answer in. If you know it for sure right away, just let somebody else put it in. All right, let me give you a minute. X to the n, what do you get over on the right-hand side? Okay, let me call in group 4. What do you have?
Okay, so we have nx to the power of n minus 1.
And your name is?
Josh.
Josh. Thank you, Josh.
Yep.
All right. What I'm going to ask you for now for the rest of the semester is when I put you in groups like this, the best answers when I get in groups, when I put students in groups and call on a group, and it works out instructionally the best, is when I don't get the correct answer. But I get something correct, but something that's a little bit off, because that's how we all work through something new. We kind of get a little bit of the idea, but there's usually something that we're kind of fuzzy about. And so then when there's an answer that's a little bit off, we can say, this was what was right about that answer, but this, do you all understand why this part needed to be changed? And people say, oh yeah. And it winds up being better instructionally if we can do that. And so what I'm going to be asking for during the rest of the semester is when I put you in groups, and you're going to have to restrain yourself, because I get all excited. When I know an answer, I just want to put it out right away. But when I put you in groups, and it's something that you're really confident about, and that you know what the right answer is right away, I'm going to have you withhold your answer for a while, and you be the last one to insert your answer. Your input will be really valuable when your group members are off and need some help. But I'm going to ask you to, instead of just putting out that answer right away, wait a bit and then respond to other people's answers and say, hey, I think you're on the right track, but look at this, and so on. And that's the kind of the way we want it.
Mr. Shankin,
Yes.
I'm like the only person in my group, so maybe can I be put in another group or
Oh, what group number are you?
number 5?
Number 5? Okay. Which group has only two people in it?
That's us, group 4.
Group 4 has only 2? All right. So how about I'll put you into group 4 now. So there's no more group 5.
Okay, thank you.
You're welcome. And is that Dominic?
Yes, it's Dominic.
Okay, that I just moved to group 4. Okay, great. Thanks for letting me know that the group weren't going to work very good for you. All right, so let me just demonstrate one more thing real quick, since this is so important. And let me take a snapshot of this. Let's put this into here. Okay. So if I took this and modified it to put nth powers in there, look at what happens. X to the nth, you get to the nth, to the nth, you get the limit as h approaches 0, x to the nth plus n, h x to the n minus 1 plus minus x to the nth over h, and then these x to the nths cancel, and you get this limit as h approaches 0, and you factor out the h, n x to the n minus 1 plus over h, and then these cancel out, and then all these go to 0 because they all have h's in them, and then you get n x to the n minus 1. All right, so that verifying this right here, which is also just following this pattern right here. So all of this that we just did, let me take another quick picture of this. All of this is what we call the power rule. And I used to think it was called the power rule because it was really, really powerful. But actually, I think it's really called the power rule because x to the power is called a power function. And so, power rule. we'll use Leibniz notation. The derivative of x to the n is n x to the n minus 1. All right. One of the other advantages of Leibniz notation is if I was using the prime notation, oftentimes that can get mistaken to think, oh, that's to the first power or something like this. And so it's, when we write out rules, I tend to prefer the Leibniz notation. All right. Now, this power rule, all we've demonstrated it for is that it works when n is a positive whole number, like 2, 3, 4, 5. It turns out to be true for any real number. It's probably quite a surprise when they first found that out, that no matter what n is, this rule still turns out to be true. So, I'm going to give you a bunch of example problems. I'm going to give you f of x, and you're going to give me f prime of x. So, let me give you, so that's x to the 1/2 power. So, you tell me what the derivative is. Use this rule, I'll give you 30 seconds. All right, so the n is 1/2. The n comes out in front. Then I take 1/2 minus 1, but 1/2 minus 1 is negative 1/2. So that's what it is. It still works out even if n isn't a positive whole number. It turns out to be true. Now, by the way, you'll often see that problem written like this. If you see x equal to the f of x is square root of x, and you're asked to find the derivative, the answer is, well, I can't do it, because this is not in the form of x to a power. You could do it with the definition of the limit, but you actually can do it even with this power rule if you realize there's a 1 here and an unwritten 2 out here. And then laws of exponent, this 2 comes underneath this, and that was really x to the 1/2. And once you realize, it could be written as x to the 1/2, then you can use the power rule to come up with your answer. Okay. These exponents, quick reminder of why this comes underneath there, is 9 to the 2nd is the same as this. And what is that 2 trying to do? It's trying to make the 9 into an 81. It's trying to make it grow larger. This 2 up here is doing the same thing the 2 up here was trying to do, trying to turn that 9 into an 81. But we know that the 2 in the bottom must be undoing that, because 2 divided by 2 is 1, 9 to the 1st is 9. We know this answer's got to be 9. This must be doing something to the 81 to get it back to 9. The only thing that we know that does that is the inverse of squaring, which is the square root. So it turns out that the bottom number is working to shrink, while the top number is working to expand and to enlarge it. And that's the same result as if we just got 9 to the first. So we know that that's correct. All right, let's do another one. Number 2, y is equal to x to the negative 5th. Now we'll use Leibniz notation for the derivative. Find dy dx. Dy dx equals, and I'll give you 30 seconds. So, the n is negative 5. Subtract 1 from negative 5, you get negative 6. So that's my answer. Now, you might say, in the end, could you put your answer like this? Because a negative exponent means bring it down into the denominator as a positive exponent. Now, you could put your answer like this. My preference, though, would be to just leave my answer like this. And the reason why I prefer the answer like this is, as we move on, you'll see a very common task you'll be asked to do is take the derivative again. And if you have it in this format, you can't take the derivative until you put it back into this format. Once you put it into the form of x to a power, you can quickly take its derivative. Otherwise, you'd have to, use the definition of the derivative to get that. We don't have a shortcut for it while it's in this format. So we prefer this format and leave it like that. Okay, let's do another one. Y equals 1/3 x to the negative 1/2. This is also Leibniz notation. Take the derivative d dx of y. This means the same as this. And let me give you 30 seconds to get your answer. Okay, now, this one had an extra complication that it has this constant in front of it, the 1/3. The one way you could do it is just ignore the 1/3, take its derivative using this rule, but ignore this 1/3 and then later put the 1/3 back in. But it turns out to be a quicker way, and it's a quick little shortcut. Is if there's a constant in front, you just take this and you multiply it by this. You get negative 1/6, and then x to the negative 1/2 minus 1 is negative 1/2 minus 1 is negative 1.5 or negative 3/2. So it would have gotten me to the same answer if I would have just withheld that 1/3 and said, the derivative is negative 1/2 x to the negative 3/2. But then I'd have had to multiply these two together anyway, so it's just a little quicker if we just, whenever there's a constant involved, you just multiply that exponent by the constant. Any questions at this point?
So I understand how we derived the shortcut using the new definition for the derivative. I guess I'm really curious as to how or why the when you showed us the combinatorics, like that second term, how does that relate? So why is that term then the derivative of the function, how does that relate to like instantaneous slope?
Ah, okay. It's a good question. Here we kind of are separating it into computational aspect. For the formal definition of the derivative, we have the limit as h goes to 0 of the rest of that. And then when you actually do it with, x to a power, like, the function was x to the fifth, we see this algebraic manipulation can get us this answer, and it's only the second term in that binomial expansion that survives that, and that winds up being the derivative. But in no way does it show that that's representing the slope. Well, that's a different way of looking at it. We were looking at it purely algebraically. We still have to link that up to, it still represents the slope, although when I'm working it out algebraically, this is the shortcut, this is how I get it. And so they wind up being, it's almost like you totally forget about it represents the slope while you're getting this, but then later on you have to link up those two ideas together. And so I think that's what's a really big challenge of calculus, and that's why it took me so long, and I had to spend so much time with it when I was first learning it. I was a senior in high school when I first had calculus, and I had never had a math class. They'd all been really easy up until then. And then this one was the first one that really pushed me. And I remember at times I would have to just stop and review everything I had learned up until that point, because it was all just kind of becoming soup. And I couldn't differentiate the different ideas. And I remember having to put lots and lots of time into it. But it really paid off. I wound up really understanding it. But yeah, it was a big challenge. And I like the way you put that question too, is that you don't think about its representation while you're doing this. But eventually you have to link that up into there. It still represents the instantaneous slope, but we're going to have long diversions about how we get the derivative. And we're going to get other different shortcuts that will be, some of them pretty nasty. But we'll still eventually have to link it up to what does it represent. It represents an instantaneous slope. All right, let's go on. Any other questions? All right, let's do another one. I'm going to take a quick snapshot here. Let's do one more. Okay, let me give you a quick minute to figure out what the derivative is. Well, actually, let me put this like this. let me stop you. Probably didn't have enough time to get through everything, but now, if there are multiple terms, there's 4 terms here. Terms are separated by addition or subtraction, and one of the properties that we looked at was the derivative of a sum or a difference is the sum of the derivatives or differences. So we can take the derivative of each one of these things separately. And so we'll just go to the first term. We multiply these two things together. Subtract 1 from the exponent. We get this. We go to the next term. We multiply the constant and the exponent together. 2 negatives make a plus. And then 7, think of it as 7 over 1, so it becomes 14 over 3. Now, negative 2/3 minus 1 is negative 2/3 minus 3/3, so it's minus 5/3 plus, and then, now this one, there's an unwritten exponent of 1 right here. And if I use the power rule on this, 1 times 6 is 6, x to the 0 power. But what is x to the 0 power? Anything to the 0 power is 1, so I don't even have to bother writing it. 6 times 1 is still 6. Now this, I didn't need the power rule to get that answer, because I know I can visualize this. See, this is when you go back to the representation of it. This is a line y equals 6x, which has a slope of 6 everywhere, so the derivative is just 6. But we could also use the power rule to get that answer. Now, this is a horizontal line, y equals 9. The slope of that is 0, so I should get plus 0. But it's also true that this is the same as 9x to the 0, because x to the 0 is 1, 9 times 1 is 9. And if I use the power rule, 0 times 9 is 0, times x to some power, but 0 times anything is 0, so then it's just plus 0, so it all disappears. And this would be my derivative. All right, now one more topic. Derivatives of exponential functions. There's a shortcut for the derivative of power functions. And we just found it. It's the power rule. But what about exponential functions? Is that an exponential function? Anybody?
No,
Why not?
because you're actually, it should be like 3 to the x
Very
instead.
good. Because for an exponential function, the exponent is in the exponent position. That's what makes it an exponential function. Okay, but even this one, we're not going to use. We're going to require the base to be e. All right. We prefer a base of e. And that's what we're going to start right now with, is the only functions that we'll learn how to take that are exponential, that we're going to learn how to take the derivative of, is when it's a base of e. Okay. Now, this function is a very unique one. The derivative of this function is itself. When you take the derivative of e to the x, you get e to the x. Its derivative is itself. Now, that has a visual interpretation. If you look at the exponential function, e to the x, if you'll remember from college algebra, it looks something like this. Y equals e to the x. And the crazy thing about this function is this. If you look at here, the x-coordinate is 0, the x-coordinate is 1, the x-coordinate is 2, now, what's the height directly above 1? Well, you just put 1 in, and what you're going to get out is e. What's the slope of this line turns out to be exactly the same as the height. The slope and the height always agree, and that's why you get the derivative equal to itself. Let me show you that again. If you take the input of 2, the height is going to be e squared. You just plug it in. Well, what's the slope? Right here going to be same as that, e squared. Let's do it one more time over here. If I put in -1, what's my height going to be? If you put in -1, you get e to the -1, which is the same as 1 over e. Now e is about 2.7, a little bit short of 3. Let me write that so it's a little easier to see. Now, if we look at the slope, right here, the slope is also going to be 1 over e. The slopes become, the heights become really, really low, and the slopes become really, really small. The slopes and the heights are the same for the exponential function. And there's if f of x is equal to e to the kx, then f prime of x, and this is just a rule that won't make any sense at this point, but you might need it in a homework problem, is the k shows up again right over here. And an example of this would be y equals e to the 5x, y prime will be 5 e to the 5x. You'd get the same thing back again, but you'd also get that constant showing up out in front. And we have run out of time, so the homework is 3.3. I will spot check that tomorrow. So you have to have it uploaded before class starts, for at least 75%. And again, a reminder, by the end of this week, go back to all of the previous homeworks. If you don't have a homework grade, and really I'm trying to give all 10s to homework grades. So if you don't have a homework grade, it tells you what you need to do. Do that. You don't need to upload the whole assignment. If it says just redo problem number 28, then you can just upload number 28, because I know everything else was fine. When I look at the comment will still be there. And I'll just look for number 28. If number 28 is there, then I'll go and put 10 in for your assignment, provided you did it right. Okay. Any questions? All right, I will see you all next, so tomorrow. And Bianca, we were going to work a little bit right after class, so let's take about a 5-minute break, and then I'll work with you. And I need to stop. You're welcome. I need to stop the recording.